Hello, we are back with a video on ray optics, and we were continuing with the case of refraction. And in refraction, as we've seen, that as light travels from one medium to another, its velocity changes. As a result of that, its with its change in as a result of the change in velocity, its direction changes, and with the change in direction what you get is for a given pair of media, that is the first medium with respect to second medium, you have fixed value of the ratio of the sine of the angle of incidence to the sine of the angle of refraction, which we uh, which we know as the Snell's law. Now, what about the case of refraction through a glass slab? So we consider a glass slab of certain thickness. Now this is the top surface and this is the bottom one. And what we will be considering is that obviously, because this is the slab, it has a thickness of T, and we consider the slab to be placed in a certain medium where which is obviously optically rarer, and the glass being the optically denser medium. So as a result of that, the light ray bends as it moves from one medium to the other, which is exactly the case over here. It is bending. Now, as it bends, it moves to the other surface. This is the refracted ray that we are considering over here. So, first of all, we will be taking this as IO, suppose, and this is suppose O dash or O prime, and then we have another normal at the point where it is striking the other face, the bottom surface, and then it is getting refracted. Now, if this is the angle of incidence that we have obtained in the first medium, in the glass medium, there is an angle of refraction, of course, and then there is another angle of refraction over here, and then again we have, for the same angle of refraction, we'll have the same angle of incidence when we come back to the first medium. So this is the first medium, this is the glass medium, which is the second. We are back to the first medium. So for that pairing, we know, of course, from the principle of reversibility that if the angle of incidence in the second medium is r, then the angle of refraction in the first medium has to be equal to I, and that means it will be, had this first ray that I have drawn, which was incident, had that been undeviated, that would have gone like this. Had there been no glass, so it would have gone like that. But there is a medium and it is suffering some refraction, and again, as it is moving from the second to the first, it is experiencing another refraction. And the reason I drew that, because this one will be again equal to I, and because this one is I and this is I as well, so these two lines obviously are parallel, that is the dashed line as well as the line that is emergent. So this is the emergent ray. I am taking OR as the refracted ray, and RE is the emergent ray, which is emerging from the other face of the glass slab. Now, because it is parallel to the initial direction of propagation of the light ray in the first medium while entering the glass slab, so we'll say that it hasn't deviated from its path, rather it has got displaced, and this displacement is a lateral displacement, which we'll be measuring by considering a perpendicular, dropping a perpendicular over to the undeviated ray. So the perpendicular line between the undeviated line of the first ray and the emergent ray, that is giving me the angle of, or the lateral displacement and that is, let us say that side is equal to d of length, and I take it as d as the point that I have dropped on the dashed ray. So from that, what we get is we have an angle over there at the top, as you can see, ROD. So this angle, well, for the angle of incidence being I, the angle O dash OD, if you look at it, that would have been vertically opposite to the angle of incidence, and that would have been completely equal to I. But out of that, the angle R is the angle of refraction that is going that has been taken out. So this angle that is left, that is equal to I minus of R. So that angle being equal to I minus of R, so we have a triangle over there, right angle triangle, RO capital D. So in right angle triangle ROD, what we get is a value sine of I minus R is equal to RD over OR. RD, that is the perpendicular which is facing the angle, over OR, which is the hypotenuse in this case, the base being OD. So that will give us a certain value. We have RD to be equal to the value D that we know of, and OR we haven't really provided any value for that, so let's keep it as such. Then again we have another right angle triangle. So in the right angle triangle, if you observe the right angle triangle O dash R, so in that right angle triangle you have an angle R, and then we have a cosine of R to be equal to the base. The base in this case is OO dash over the hypotenuse, which is the common OR side, and OO dash, as you know, is equal to the thickness of the glass slab, which is equal to T, and is the OR is the hypotenuse that we have taken. Now if we take the ratio of both these equations that we are getting over here, what we get is, on the left hand side we have sine I minus R over cosine of R to be equal to the value being D over OR at the top, and the denominator just reverses. So OR, they get cancelled out, you have D over T. So the value D here will be equal to T times of sine I minus R. You can just take the 1 over cos R to be cosine of R to be equal to secant of R, that is sec R. Well, the angle of incidence and refraction, if they are maintained, then you have the case of D to be dependent on the thickness. So the lateral displacement will be more if the thickness of the glass slab is maintained, is more. If the thickness of the glass slab is less, then the lateral displacement would be less. We will keep this in mind because we'll be using this condition of greater or lesser thickness uh, after some time when we'll be studying about thin lenses. Now in this case we can also modify this equation over here a little bit. Well, as far as the cosine of R is concerned, what we can do is we can, in order to bring the refractive index into consideration, what we can do is we'll just we'll just use the trigonometric identities. That we can do a lot of things. We can divide this equation that we have at hand over here. I'm writing the right hand side of the equation first. So this is d over t, and as far as the right hand side, now we have sine, we expand that, so we have sine I into cosine of R minus cosine of I sine of R over cosine of R. Now what we do is we can, well, we can just get rid of that cosine of R as of now. So we have sine I cosine of r gets cancelled with the first term, and as far as the second term is concerned, we have cosine of I tangent of r. Now what we can do is we can just divide this entire equation and multiply at the same time by a factor sine of r. So what we are going to do is we'll keep the d over t on the left hand side. We'll just divide this equation over sine r, cosine of I tan of r over sine r. Now we cannot just do that at our own will. We'll have to multiply a sine of r as well, because we are dividing one, so we must multiply one. So now what we have is we have a mu, which is sine I over sine r, which is the refractive index of the material of the given glass slab, minus, well, as far as this equation is concerned, what we can do with that is we can keep it as such, but also we have to multiply that sine r which is outside. We'll do that later. We'll just put the values first. Cosine I tangent of r over sine r, and all of that multiplied to a sine r outside. Now that comes in, we have a d, we get the t multiplied, and we keep the bracket as of now. We have mu times of sine of r which has gone in, and if it goes in the second term, we have cosine of I tangent of r. The sine of r that we had multiplied and divided, they cancel out, and so we have t times of mu sine r minus cosine I tangent of r. Now one thing that we can use to our benefit is that if we have the value of mu provided to us and we do not know I and r, so we can get rid of either of them in this case, in case we have only the I terms. So we know that sine I by sine r is going to be equal to mu. So in case we do not have any value of I or r, we can substitute uh, the other way around, because we know that mu is equal to sine I by sine r, and we can substitute any value for any value in the equation and get get it get the answer, provided they are known trigonometric angles, else you will have to use a trigonometric table. In this case, again, we can also have sine I to be equal to mu sine r, and therefore you have cosine I to be equal to 1 minus mu square sine squared r, because you are squaring both these sides and you are subtracting them from 1 and taking them under root, so this will be under root. So you can use this value over here for cosine of I, although it may look pretty clumsy, but still, uh, provided you are given only the angle of refraction which is of a known value, you can use it and obtain the result. Uh, so likewise, there are various processes in which you can use these trigonometric identities to your own benefit in order to find the value. Okay, so let's move over to the next part, which deals with the case of real and apparent depth. So here, if we have supposedly a beaker which is having some amount of liquid in it, and then we have placed a coin over here. And now obviously, in order to see the coin, you will have rays to be emanated from that, and one of those rays is supposedly moving like this. Now as it is traveling from an optically denser to a rarer medium, it will be bending a bit away from its course. That is, it will be bending somewhat like this probably, and there will be a certain angle of incidence in the denser medium, and there'll be an angle of refraction in the rarer medium. As a result of that, what happens is that one of the rays probably may be considered along this line, and as this ray is considered to be coming straight to an observer who would be viewing like this, then he would think as if the coin is probably present over here. So this is what appears to be at this depth, which we can take as A, that is the apparent depth. And this is actually the real depth at which the coin is exactly placed below the surface level of the liquid. The liquid will have some refractive index of its own. We'll come to that later. But as of this case, what we get is, again, we'll have this entire angle. Let me use another ink for that so that it's visible quite clearly. Uh, in fact, I can zoom it as well. I'll be doing that. So let me just zoom. Now, this angle that you see over here that I've just drawn, that is vertically opposite to R, and that is that is R. So there's another small angle. I'll be zooming it, and I'll use another ink for that. The red one seems better. So this angle that you see over here, that red angle is nothing but equal to I R minus of I. I don't think we would be requiring that. I'll drop it as of now. I'll see if whatever we have is sufficient for us. We'll keep it to the angle R. So now, if that is equal to R, then this angle would be equal to R as well, because they are interior alternate angles. And if this angle is equal to I, this angle must be equal to I as well. So you have I and R to be having a common base. Now, if you look at that, I'll be naming the sides over here. So this is probably O, this one's A, this one is B, and this one is C. Now, all these angles that I have considered, the angles considered are small. Because they are small, sine of a given angle for sine theta goes to theta for smaller angles, and it can also go to tan theta as well. Now let's consider the case of tangent of these angles, of these I and R that we have got over here. Tangent of I in this case is in the triangle that is you can take CAO, the triangle CAO. It's a right angle triangle with the right angle at the point C. So tangent of I in that case is equal to the perpendicular CO over the base, which is equal to CA, that is attached to the angle. And as far as tangent of R is concerned, we'll consider the right angle triangle CBO, and in that case it will be CO over CB. Now if we take the ratio, then we have tangent of I over tangent of R to be equal to CO over CA, and this becomes this just reverses, so CB over CO, they cancel out. We have CB over CA. Now the tangent can be taken same as that of sine, for smaller angles. So this is nothing but sine of I, that is the angle of incidence, over sine of R, angle of refraction. And CB, as you know it, is the apparent depth over CA being the real depth. Now, for the refractive index of the medium concerned, we will obviously be dealing with the refractive index of the denser with respect to the rarer, and that, let us say, is a mu. Now, because the mediums have been taken in the other way around, that is the light to be moving from the denser to the rarer, which is usually the other way around in the derivations that we have considered so far. So what we can get is actually this is the refractive index of the rarer with respect to the denser in this case, which is equal to 1 over mu, or 1 over denser with respect to the rarer, which we have taken as mu over here. So 1 over mu is equal to A over D. So we have the refractive index of the liquid to be equal to D over A. Now it is quite easy to consider, easy to identify whether you take it D over A or A over D, because the apparent depth will always be less than that of the real depth. And when you have A over D, that means you are going to consider the refractive index of an optically rarer with respect to an optically denser medium. And when it is d over a, that is the real depth over the apparent depth, it is definitely going to be greater than 1, because the real depth will be more than the apparent depth. And in that case, you are obtaining that to be the refractive index of an optically denser medium with respect to an optically rarer medium. So it is quite easy, if you know the physics of it, that how and why we are considering the lengths and the refractive indices that are associated with them. So if you know the physics of the denser medium to be having a refractive index greater than that of the rarer medium, then you will be able to remember this equation correctly. Now also we can determine the shift in the height. Now if the shift in the height is taken as x, then shift is equal to the real depth minus the apparent depth. Now the real and apparent depth are related to the refractive index of the liquid as this. It can be liquid, it can be anything, but from the example I'm considering it as liquid. So you can either have d to be equal to mu times of a, or you have a to be equal to d over mu. Take it as you like. So you have the shift to be equal to the real depth. You can put that value, and you can use the apparent depth as d over mu. So you have d as the common value, so 1 minus 1 over mu. This is usually the preferred equation for the shift, because you always know the actual depth rather than the apparent depth. So apparent depth is the one that you are trying to determine, or you are trying to determine the shift that may come your way, or you are trying to determine the refractive index in case you know the shift in the position. So either way around, you can calculate various values associated with the parameters that are available to you. I'll give you a small example. Suppose we are considering a glass cube, and it has trapped a certain air bubble in it. Now, as it has trapped a certain air, the glass cube is of certain dimension. Obviously, it's a cube, so it'll have the same length for each of its edge. Now, from the front on view, it looks like a square. Now, what happens is that if a person looks from the top surface, he finds the apparent depth to be somewhere at a distance of 2 centimeters in depth. And when he views it from the bottom surface, The apparent depth seems to be at a distance of about 4 centimeters. The question is, what exactly is the thickness of the cube, or one of its dimensions that we need to know, the length of each side of the cube. Now, it's given that the refractive index of the glass in which the air bubble has been trapped is supposedly 1.5. So here's an air bubble trapped in a glass cube. So in order to determine the length of each side of each edge of the glass cube, what you need to know is you need to know the thickness. Just the thickness would do. That will be the length of one of the edges, and this is a cube, so all the edges will have the same thickness. So how to determine that? Well, you have a depth, certain depth, real depth d1 for the first case, top surface, and you have a certain depth d2 from the bottom surface where the apparent depths have been provided. So d1 here will be equal to mu times of the apparent depth a1 probably, which is 2 centimeters, and a2 is supposedly 4 centimeters that we have taken. So this is 1.5 times of 2 centimeters, so this is going to be 3 centimeters. And as far as d2 is concerned, d2 will be equal to mu times of a2, which is equal to 1.5 times of uh, 4 centimeters, a double of that, which means 6 centimeters. So the total length of the edge will be equal to 6 plus 3, which is equal to 9 centimeters in thickness. So that will be the length uh, of each of the edge of the cube. And supposedly you have been asked to obtain the volume of such a cube, then you can always take the cube of the length of each edge, and you'll find it to be equal to 729. So these are some of the cases that you deal with the refraction in glass slab, or in case of real and apparent depth. This was just a one of example. You can deal with many such more problems, even the layering of a few slabs that you can deal with. We'll be discussing those in the next video. Till then, thank you for watching.